Good morning, everyone. I want to welcome you to my lecture today. Of course, today we're basically going to finish chapter 8. Earlier, I said I'm actually going to have 4 lecture series, and this is going to be the 4th one, and it's going to be the last one in chapter 8. On Wednesday, I'm actually going to walk you through the midterm 2 practice questions. And of course, the data set for one of the questions that is called popcorn has actually been published. I need you to check the week 10 model. Okay, you're basically going to see that. The midterm 2 will be written in person, and every instruction that we have for midterm 1 we also go with midterm 2. Okay, so today, like I said, basically I'm going to walk you through the last lecture series in chapter 8 that we call additional topics in Anova part 4. And of course, in the outline, I'm going to walk you through Anova and regression with indicators. Let me tell you this. There's a relationship between analysis of variance and regression analysis. Do you know that at times what you want to achieve with linear regression, we can also achieve that with the analysis of variance. So today I'm actually going to show you, okay, how they can be used interchangeably in a particular situation. So I'm basically going to talk about the one-way ANOVA. For means as regression, I'm also going to talk about two-way ANOVAs as means as regression. And finally, I'm going to walk you through what we call the analysis of covariance. You've done analysis of variance. What makes analysis of covariance different from analysis of variance? Now let's get started. I want to start with the ANOVA and regression with indicators. This is the situation. Let us take a look at the analysis of variance. In analysis of variance, we're basically looking at the effects of categorical predictor on the response. But in analysis of variance, we call the categorical predictor factor. If it is one factor, we call it one-way analysis of variance. But in regression analysis, do you know the same way I can actually compare groups, means in different groups where we have one factor? We can also do that with a linear regression, where we're trying to look at the effect of categorical predictor on the response. It's the same. I'm going to say this again. When we're comparing, I'm going to start with this. Let me start with two populations. If I'm comparing means in two populations, you know what you normally use. If the assumptions hold, assumptions of what? Normality hold. Of course, we use t-test, right? I know some of you are familiar with t-test. We use t-test when we're trying to compare means in two populations. And you know what? When the assumptions of normality hold, you use t-test. Do you know that that same test, you can also achieve that with a regression analysis? How? In the regression analysis, if I'm looking at the effect of categorical predictor on the response, where the categorical predictor has two levels. I'm going to give you an example now. I'm trying to look at the effect of gender on salaries, male and female. If I want to use linear regression, then that is called regression with indicator. What I mean by indicator, it means the predictor is categorical. Do you know I can also do the same with a t-test? What am I doing with a t-test? Oh, I can say I want to compare the what? The means, that the salaries, the average salary of male and female. Look at that. It's the same. Linear regression with indicator is the same as a t-test of comparing means. I'm going to say that again. Simple linear regression when you have a predictor that has two levels is the same as conducting a t-test where you are comparing means in two groups. They are the same. That's what we mean. Okay. Now, I want to walk you through. You remember this particular data set. We've used this data set before. We got 5 levels, and we're trying to compare longevity in 5 groups, right? We want to make use of this data. I'm going to show you the data set again. Take a look at that. This is just 1 to 6 of the data set. We got a lot of variables here, but we are only interested in longevity and the treatment. We got five different groups. The treatment, the factor is categorical, right? Okay. Now, you know what I want to do now? I want to compare 2 groups. Out of the 5 groups, we have some are virgins, some are pregnant, and some are none. When you're talking about the fruits, flies that we're talking about here, and we basically want to compare longevity in 5 groups of fruit flies. But let me tell you this, we only want to compare 2 at a time now. Like, I want to look at 8, okay, virgin with none. Of course, if I want to compare 2 groups in statistics, 2 groups, provided normality, assumption hold, what am I going to use? T-test. Okay. Now, I've used t-test. Take a look at that. T.test. You see, T.test, 8, none. 8, none. If you take a look at what I have, T.test. Oh, this of you online, can you confirm if that is changing for you? Is it changing? Is the slide changing? I need someone to confirm that. If that slide is changing.
Yes.
Oh, thank you so much. Thank you for confirming that. Okay, now I have conducted a t-test. Why am I conducting t-test? Because you are comparing means in 2 groups. Now, what happened here? Take a look at the p-value. Because the null hypothesis is going to tell you the 2 groups are the same, like the means in the 2 groups are the same. And the alternative is going to tell you they are not the same. Take a look at the p-value here. The p-value here is very, very small, right? Which means you're basically going to reject the null hypothesis, which means there's a significant difference between the longevity of 8 virgins and none, right? It's a significant difference between them. And if you want to look at the confidence interval, I told you when the confidence interval is between negative and negative or positive and positive, then a 0 does not, a 0 is not included in the interval. When a 0 is not included in an interval, you know what that means? There is no significant difference. I mean, sorry, there is a significant difference. I say, when here now, there is no 0 in this interval. Then what that means, difference exists. That is the meaning. The only situation where there is not going to be any difference at all if when you have from negative to positive. But now it's from negative to negative. So which means this is in accordance with the p-value. Take a look at that. Okay, that is in accordance with the p-value. And of course, you can really see the mean. The 2 mean that we're comparing. Of course, 38.72 is far from 63.56. So which shows, this result and that result is actually right. You know what I've done here? I use the idea of a t-test. What is another idea that can be used? I'm going to show you. Now, if I don't want to use a t-test, I can also use simple linear regression. And I'm going to show you now. Now, the question now is, am I going to have the same decision with a t-test if I use simple linear regression? Now, we said there's a difference here, right? Let's use simple linear regression now. Oh, look at the simple linear regression now. What am I doing? Longevity on that. The V8 is what? The V8 is categorical, right? I have a categorical predictor, right? It has 2 levels, right? How many levels is going to be reported in R? Just going to be 1. Look at that. You remember the other time when you have a linear regression, and if you have 3 levels, it's going to report 2. Okay, now it's reporting 1. The other one that was not reported is being referenced. I think you remember. This is a simple linear regression with a categorical factor. What I'm trying to tell you now is if the predictor in a simple linear regression has 2 levels, then you can alternative tests that you can conduct instead of conducting simple linear regression is a t-test. Now let us have it now. Oh my God, it's significant as well. Look at the p-value. What is happening here? Regression analysis agree with the t-test. Look at that. You can now see linear regression with categorical factor. Okay, where if the factor has 2 levels, then is it the same thing as conducting a t-test? That is what I've just demonstrated. Is there anyone who needs clarification on this? Is there anyone either in person or online? Okay, simple linear regression with a categorical factor, where the factor has 2 levels. Anywhere in the world is the same thing as t-test. You can conduct a t-test, but there's one condition to conduct a t-test. The 2 groups have to be normally distributed. I showed you the other time. This is a pure wiki test. If it is not, you go for non-parametric, like Wilcoxon test that I walked you through the other time. And you also know in simple linear regression, residual has to be normally distributed as well. Look at that. Normal distribution here, normal distribution in the other one. What of in a situation where we have more than 2 levels? We know when we have more than 2 levels, we can use one-way analysis of variance, right? We can also use multiple linear regression, which I'm going to show you. I'm just trying to tell you the kind of different, the similarity between linear regression and analysis of variance. Let's take a look at this. What am I doing here? I'm trying to compare longevity of 5 different treatments. That is why the degree of freedom is 4. Because 5 minus 1, you're comparing whether the longevity is the same. What am I doing here? This is a one-way analysis of variance in R. What is the p-value telling us? The p-value is less than the 0.05 level of significance. What are we trying to say? The null hypothesis is rejected. It means the longevity of the 5 treatments is not the same. And that is why you say the p-value that way. Now, take a look at this guy now. I want to, instead of me to use one-way analysis of variance, okay, I decided, it is not, I think I need to correct something here. It's not going to be multiple linear regression, I'm going to tell you. It's just still going to be simple linear regression. You know why? It's going to be simple linear regression, except that the categorical variable, how many levels? 5. I'm going to correct that. It's not multiple. It's simple. But only that, what is the levels of the categorical predictor? 5. And that is the reason, what I'm trying to do here, I'm trying to create those, because of the way, maybe the reason why I call it multiple linear, I'm going to tell you why I call it multiple linear. I think when you see calling multiple linear, maybe we're still fine. There's no problem. Maybe the way I coded my data, the way I coded my data, if you take a look at this, what am I doing here? What does it look like? This plus, that's a multiple linear. Let me leave it that way. Because you have P1, V1, P8. Well, I'm considering 4 out of 5. I'm only considering 4. The 5th one is none. No virgin, no pregnant. You can say I have P1, V1, P8, 4, 8. I'm considering the real treatment. Out of the 5 levels of treatment, one of them is placebo, that control. I'm only considering 4. Now I'm looking at that as a multiple linear regression. Now let's look at the results. This is the result. Now, there's something that is very interesting that I wanted to say. Tell me, which of this is significant? Just this guy here, right? When we're conducting the other time, when we only consider this guy as none, which one is significant? Let's go back. You see, is it significant, right? V8. You see that? Even when I compare with the other one, when I run the other one, it is the only one that is significant. Look at that. You see that? Okay. Now, you have seen the similarity between conducting t-tests, analysis of variance, conducting t-tests and linear regression, and conducting analysis of variance and the multiple linear regression. You know what I want to do now? What if in a situation where we have 2 factors? In analysis of variance, I've worked it through what we call two-way analysis of variance, with interaction, without interaction. Don't also forget, I've also walked you through multiple linear regression without interaction and with interaction. Do you remember that? We've done the same. I'm going to repeat myself. I've walked you through multiple linear regression model with interaction, without interaction. I've also walked you through analysis of two-way analysis of variance with interaction, without interaction. And I want to walk you through something now so that you're going to see there is a similarity between the analysis of variance and linear regression. Now take a look at this. I want to look at the effects of 2 categorical factors on the weight gain. Weight gain is a response. Antibiotic, is either you use antibiotic or not, yes or no. B12, yes or no. Each of the factor has 2 levels. I'm going to say that again. The 2 categorical factors that we have here, each of them has 2 levels. Now, do you know that when you have a data set like this, as an analyst, 2 things is going to come into your mind. Am I going to use regression, or I should use analysis of variance? I'm going to say that again. That is what is going to come to your mind. Am I going to use regression, or I should use analysis of variance? But let me tell you this. You can use both regression and analysis of variance, but I'm going to tell you now, the analysis of variance has more statistical power in a situation where your data set, where you conduct an experimental studies. I'm going to say that again. Mathematically or statistically speaking, There is no difference between analysis of variance and regression analysis anywhere in the world. But where any of them could have advantage actually depends on the nature of studies. Regression analysis are more appropriate for observational studies, while analysis of variance are more appropriate for experimental studies. Okay, now you have a data set. You want to look at the effect of whether I use antibiotics or not, or I use B12 or not on weight gain. Okay, let's first start. I know you're going to go with the two-way analysis of variance, right? That because you got two factors, right? Now, what am I doing here? Of course, I'm trying to, trying to import my data into how that data is from the textbook. When you want to import any data from that textbook, don't forget you're going to load start to data. Don't forget. And after loading the library, start to data, there you're going to, the name of that data, you're going to write data parentheses, the name of the data file. Then you're going to attach. You can see I have, now what am I doing? AOV. Oh, I'm doing analysis of variance. Then this is two-way. Then what am I doing here? This plus that is more or less like two-way analysis of variance without interaction. What do I have? Oh, it is only B12 that have effect on the weight change. Antibiotics does not have effect. Take a look at this. Whether you use what this result is trying to tell you using the analysis, using the two-way analysis of variance, whether you use antibiotics or not, it does not have effects on weight change. What has effect on weight change is B12. Because the B12 is significant. What did I use here? What kind of model? This is two-way analysis of variance. If I decided I don't want to use two-way analysis of variance, I decided I want to go in the direction of regression. Let's see what is going to happen. What am I doing now? If I want to go in the direction of regression, of course, I need to create two-way effects. Because I have two factors. I'm basically going to have two predictors. The first predictor, okay, and it has to be numeric. Okay, numeric, I said antibiotic equal to what? Yes. When you are using antibiotic, it's going to be yes. When you are not using it, it's going to be no. I got A here for antibiotics. I got B here for B12. Oh, what am I doing here? AOV. Now change to LM. We are no longer using AOV. We're no longer using analysis of variance. What are we using now? Linear regression. What is it? What is this in? This is a multiple linear regression with two predictors. Let's see the result. Summary. What is the result? Oh my God, look at that. B, what is B? B is significant. What does B represent? B represent B12. Don't forget, when you fit two-way analysis of variance, B12 was significant as well. What are we talking about? Two-way analysis of variance is the same as multiple linear regression with two predictors. You're taking the same decision. Take a look at that. You're taking the same decision. Take a look at that. Is there anyone who has any question? If they are taking the same decision, then what is the difference between analysis of variance and regression? Let me tell you this. Analysis of variance is more appropriate, has more statistical power. If you have experimental studies where you assign participant into group randomly, like you're talking about weight change here, and the participants you use, the experimental unit you use, you assign them into category, like in the antibiotics, you deliberately, you assign some into, they shouldn't use antibiotics, some should use antibiotics, and in the B12, you assign them into the group randomly. That's an experimental study. If you use analysis of variance or you use regression analysis, you're going to get the same results. But you know what? Despite the fact we're getting the same results, our conclusion in terms of, like, when you look at the analysis of variance, the idea of you can conclude in favor of causation, cause and effect, but you can't do that with the regression analysis. In your regression analysis, you are only measuring effect. Association is their association. You don't say this caused this. With the regression analysis, you can't say my weight did not change because I did not use antibiotics, or my weight did not change because I did not use B12. No. Here, you know what you're talking about here? You are only looking at the effects. Effect does not mean this caused that. No. The conclusion in linear regression, despite the fact they are giving the same result, the conclusion is different. For linear regression, it is association. You can only talk about association with linear regression, but with the analysis of variance, you're talking about causation. This is for ANOVA, this is for regression. This is going to tell you, oh, association, the relationship exists. But that doesn't mean this caused this. No, it is only here with the analysis of variance. Okay, now, do you know that we've done something before where after running your linear regression, we normally go for what we call ANOVA for regression, where you're going to say ANOVA into. You remember that we've done that before. What is the essence of doing this? The essence of doing this, guy, is basically to see whether relationship, like if you really want to know what is the percentage of contribution of the treatment, because we believe that there is 100% variation in the response. What is the total explained variation? If I want to know, this is treatment A, treatment B, the total explained variation will be this guy plus this guy. The unexplained variation is this. Look at that. This is the unexplained. So the essence of this is basically to partition, to split the total sources of variation into various components so that you'll be able to say the one that is explained by each of the treatments. So that is where we do this. Now, the other time, we are still on the same concept. We've looked at the two-way ANOVA without interaction. Let's now look at two-way ANOVA with interaction. Antibiotics, B12, and the interaction between them, because the reason why we needed to test for the effect of interaction, there is possibility that the relationship between a response and a particular predictor may depend on another predictor. And I've walked you through this before. When interaction is significant, then it should be, its inclusion in a model is justified. What happened now? Okay, go ahead. That's a very nice question. I wanted to look at the code. You can say antibiotics, B12, and what? The multiplication, which is the interaction between them. Okay. Now, that is what I included in the code. Now, when I include that in the code, that will enable me to test the effects of the this guy here and this guy here, we call that main effect. The main effect is talking about the individual effects. Now, what do we have? The interaction. You can see it in my code, right? What do you see? What happened to the interaction? It is significant. Okay, I got what you mean. You are trying to say, am I going to get the same result if I now do B12 times antibiotics instead of antibiotics times B12? Oh my God, commutativity is the same. It's like 2 times 3 and 3 times 2. They give 6, right? So it's going to be the same. So whether you say x1 multiplied by x2 or you say x2 multiplied by x1, they mean the same. Does that make sense? Yeah. Okay. Now, this is two-way ANOVA, right? With interaction, right? Let us also look at the multiple linear regression with interaction for the same problem. Let's go there. What are we doing now? We are back at multiple linear regression with interaction, right? We've done two-way ANOVA with interaction. What do you see? You can see LM, right? LM. Okay. What happened at the end of the day? The interaction is significant. Whether you do the multiple linear regression with interaction or you do the two-way ANOVA with interaction, you see what happened, you get the same result. You see that? Okay. And the next thing you can do here, you can do ANOVA for regression. Of course, what ANOVA for regression is just going to do for you is what is the contribution of each of the predictor. That is what you see here. That's how you're going to see sum of squared. This is like the contribution of A, the contribution of B. If you want to look at the total explained variation is going to be this plus this. Unexplained, total explained variation is going to be this plus this plus this because you have to include. So all these ones, why this is going to be unexplained. In case you want to get your R squared, okay, take a look at that. Now, you know what I've justified today before I go into the next topic. There is a similarity between the analysis of variance and the linear regression. But what determines what you're basically going to use is the nature of your study. Do you have experimental study or do you have observational study? When you have experimental study, you go with the analysis of variance. When you have observational study, you go with the regression analysis. And that is the reason why the way you collect your data set is very, very crucial in statistical analysis, because the mode of your data set, the nature of your data set will determine the appropriate statistical methodology you're basically going to use. We care to know the source of your data. Okay. The second objective of the day. We've been talking about analysis of variance. We also have what we call analysis of covariance. You remember in linear regression, right? When you are looking at the effect of a predictor on the response, if there exists another potential variable that could have effect on the response, what are you going to do? You're going to consider that, right? Now, let me tell you this. In analysis of variance, predictor has to be categorical only. I'm going to say this again. In analysis of variance, your predictor has to be categorical. But let me tell you this. We got situation whereby we can also have In addition to categorical predictor, in analysis of variance, we can also have a continuous predictor. When you have a continuous predictor or the quantitative predictor, we are no longer talking about analysis of variance, but we are talking about analysis of covariance. Look at that, covariance. Now, I'm going to give you this example now. Auditing data collected by Kuttner et al. 2005, where the accounting firm want to study the effectiveness of 3 different methods for training statistical auditors. They have 3 methods. Method A, where the auditors they study at home with the materials provided. Method B, the auditor trained in a local office with local staff. Method C, the auditors train in Chicago office, which is happen to be the headquarters, right? You know what we want to do? They basically want to compare the effectiveness. They want to see whether these 3 methods, whether they are the same. When the staff get trained at home with materials provided, with a staff that get trained in a local office, with a staff that get trained in a national office. Now, let me tell you this. You know what we have done? Why is it ANCOVA? I'm going to tell you. Why is it not analysis of variance? I'm going to tell you. You know, in the analysis of variance, before you can use analysis of variance, you're basically going to you're going to compare the post test, the test, because after the training, the auditors are going to write exam. If you are using the post score only, then you are actually going to use analysis of variance. What they did here, they have a total number of 30 auditors, and they have 10 for each group. Before the training, before they receive training at all, they have a record. They know their record, pre-test. That's what they call pre-score. And after the training, they have another score. I'm going to show you now. Take a look at this. Do you see this? This is for method, for different training, whether training local office, training Chicago. If you are only using the score here, after they've been trained, they gave them exam. This is their scores. If I'm only putting into consideration this alone, the post alone, then I'm going to do analysis of variance. But right now, we realize that the effect, like pre-score, even before the training, could potentially affect the response. And that is the reason why we're basically also going to consider this. Considering this, that is the covariance. That is what makes it analysis of covariance. Because we are also considering the pre-test, not only the post-test. Okay, now, if you take a look at this, give me 1 second. Now, if you take a look at this score here, this is the even before they wrote the test at all. Before they wrote the test, this is the average score. After writing the test, before the training, this is before the training. What you see here is before the training. And what you see here is basically after the training. Okay? Now, now I want to bind that. Well, let me tell you this. If you want to use analysis of covariance, we have assumptions. Number 1, assumption that we need to check. There must be linear relationship between X and Y. What is my X? What is my Y? My Y is the response. X is the covariate. In analysis of variance, we don't consider quantitative predictor. The X X that you see is a quantitative predictor. Before I can consider analysis of covariance, there must be relationship between the response and that covariate. That covariate is X. Then another assumption is that the parallel slope assumption is reasonable. What we mean by the parallel slope, it means at different levels of the treatment, okay, the relationship between the response and that covariate has to be the same, has to be parallel. That's what we mean. Then another assumption is that the covariate X and the treatment, okay, they should not relate. There shouldn't be any relationship between the categorical predictor and the covariate. We have a way to test that. And the last assumption is that homogeneity of variance, which I'm basically going to quickly walk you through. Take a look at this. What did we just say? Before we can incorporate covariate in analysis of variance, that covariate must have what? Must be significant. Now, post is the response. Pre is the covariate, the quantitative covariate. Now, let's see what happened now to the pre. What happened? It is significant. Because of that, I'm actually going to incorporate covariate into the analysis of variance. Incorporating covariate into analysis of variance, it becomes analysis of covariance. Covariance. Now, this is a justification. After this, the next thing I'm going to do now is going to be testing for absorption. Okay, what am I doing now? There shouldn't be any relationship between the covariate and the categorical predictor. How am I going to test that? Then it means I'm going to test for the interaction effect. Look at that. There shouldn't be any interaction effect. The covariate and the categorical predictor must not have any relationship. That is the rule. If they do, then we cannot use the analysis of covariance. And that is the reason, what am I doing now? Pre multiplied by method. Pre is the covariate. Method is a categorical predictor. There must not be any relationship between them. And the only way to test that is to test whether their interaction is significant. What I'm trying to tell you now, in the analysis of covariance, interaction between the covariate and the categorical predictor should not be significant. Let us now see. Oh, look at that pre-method. It is not significant. The assumption hold. What I've just demonstrated now, the interaction between pre and method should not be significant. Now the assumption hold. Now the next thing to test is the relationship between now I'm not going to run. Now, if you take a look at what I'm doing now, okay, I basically trying to see, is there any relationship between that and that? This is another to show. If you don't want to show by interaction, can we say there's a relationship between the covariate and the categorical predictor? Okay, what do you see? At the end of the day, it is not significant as well. Now, if it is not significant, the next thing is to test whether the assumptions of homogeneity of variance hold. You use a Levine test, right? You remember you conduct a Levine test. What is the p-value? It's not significant. Assumption hold. Now, the next thing, go ahead and fit the analysis of covariance. Okay? In fitting the analysis of covariance, if you can first fit the analysis of variance and see. What am I doing here? Post on method and fitting the analysis of variance here. Post on method. Method is significant, but you know what? If I fit this alone, okay, it's basically not going to be fine. You know why? Because pre, which is a covariate, is significant. I need to incorporate that into the model, and that is basically So when you incorporate that, that is what you basically do here. Give me 1 second. Here, you can see that the pre is, so you can see that there. So at the end of the day, what you see now, you basically see that when you have already adjusted for that and you incorporate the covariate, you can see that the method is now significant. And at the end of the day, if it is significant, you can do a multiple comparison test. Comparing the method B and A, C and A, and C and B, what happens? You look at the p-value. It means the difference that exists is between C and A, those staff that get trained in their house with the document the material provided, and C, those staff that get trained in the national office in Chicago. You can see the p-value is very, very small. And when you take a look at it, the p-value is very, very small. But here, there is no difference between those who is trained in the local office and those who get the material provided, who get trained at home. Okay. And finally, let me show you the results of the analysis of covariance in general. Pre as a covariate method. What happened to them? The two of them are significant. What I've done to you now, what I've shown to you now is what we call the analysis of covariance. The way we run analysis of covariance is different from the way we do analysis of variance. The difference between the analysis of covariance and the analysis of variance is just that in addition to the categorical factor, you have a quantitative predictor as well. And the only way you can tolerate the quantitative predictor here is a pre-score before the staff undergo training at all. Now, let me quickly tell you what I did in one of my capstone projects. What I did in one of my capstone projects, I work with somebody, a colleague from the veterinary medicine. We are looking at the effect of some selected treatments on the weight gaining ability of pigs. You know what we did? We use analysis of covariance, because when you are talking about weight gain, you look at the initial weight as well. You don't only look at the final weight. You know, when you are looking at the final weight alone, when you are only looking at the final weight, you could mislead. That is, you're doing analysis of variance. But in addition to the final weight, we also consider the initial weight of the animals. Even before you introduce the new feed, what was the initial weight of the animal? The initial weight of the animal is going to act as a covariate, because the initial weight of the animal could have effect too on the weight gain. And that was the reason why you can see the other time we tried to investigate whether the pre-score has effect on the response, and you see it was significant. And we also have some assumption that shouldn't be relationship between the pre-score, the covariate, and the treatment. There shouldn't be any relationship between them. You saw the way we did it before you now successfully construct your ANOVA. Okay, I want everyone to be present on Wednesday, because what we're going to do, we want to have a preview on the midterm 2 practice question. And I'm going to give you a lot of information. If you attend our review on Wednesday, I can assure you, you are not going to have any problem at all completing that midterm 2. And I'm also going to do the same review for the final exam too. That is what I've been doing. So make sure you stay safe and have a very beautiful day.